So for our first example of an integral done in spherical coordinates, we're going to take it easy. We're just going to look at setting something up over the unit ball. And it's going to be this integral right here. So the integrand is e to the x squared plus y squared plus z squared, all raised to the power of 3/2. Okay, which looks horrible, except when you start looking at it through the eyes or through the lens of spherical coordinates, and you say, oh, look at this guy right here. That's actually rho squared. So if I do rho squared and then apply a square root to it, those are going to cancel. So this whole exponent is just going to end up being rho cubed, which gets suddenly much, much more simple. So let's see how to set this thing up here. So when we look at a ball in spherical coordinates, the way to envision like what's going on with spherical coordinates is you want to say, okay, so we extend our radial line segment up vertically to whatever the radius is, so rho out here, our upper bound for rho. And then we're going to sweep it down through some arc, passing through the positive x-axis and then clipping onto the negative z-axis. So now, at this point, you envision there's like this solid semicircle that's had stuff swept through it. Right? Okay. So imagine this little like lamina or whatever shaped like a semicircle, half a disc. And then we're going to take that and we're going to rotate it around the z-axis, like in this following this circle. And so as that thing goes, so like for some positive theta, it's going to look, there's our semicircle, and then for some other positive theta, it's going to be over here whacking through the positive y-axis, and then eventually we'll get over here to the negative x-axis, and then we'll be spinning out into the hinterlands and further and until it like ends up having swept out the entire ball. So that's the little like animation that should play out in your head for trying to see how the coordinates work and how to set up your zone. So our region of integration for this one, let's see. So the radius is going to be what we do first. And in this picture here, this region reaches all the way to the origin at the core. Or said differently, when we extend that blue line up the axis, the first place that it hits the ball is right where it actually starts. So we start at 0 and we go up to the outer end. This is a ball of radius 1 because it's the unit ball. So we go from rho equals 0 up to rho equals 1. And then we say, okay, so now how far down did we swing through an arc? And we went all the way, so we started it all the way at the top and we ended all the way at the bottom. So we started at phi equals 0 and we went all the way through an angle of pi over 2. So we go from phi equals 0 to phi equals, I'm sorry, I said pi over 2, I meant pi. We go all the way to phi equals pi. So that's our second integral. And then for our third integral, we take it for a spin through the whole circle. So theta goes from 0 all the way around the back to where we started at 2 pi. All right, so there's our triplet integral. And this is going to be, let's see, so we have our e to the rho cubed, as we discussed before, times our Jacobian rho squared sine phi. And that was rho first, followed by phi, followed by theta. And that's typically the order that you set up a spherical integral in. It's fairly unusual to do it in a different order. Could happen, but not so often. Okay, just for variety's sake, let's go ahead and evaluate this one out completely. So let's see. So now actually, here, I'll just rewrite it real quick, slightly neater and without the variables. So it's 0 to 2 pi, 0 to pi, 0 to 1, e to the rho cubed, rho squared, sine phi, d rho, d phi, d theta. And one thing that you notice is that in spherical coordinates, a ball is actually a rectangle, right? Those are all constants. So we look at that and go, oh, you know what? And this function actually splits apart into a function of rho only times a function of phi only times a function of theta only, which is just like the function 1 here, 1, just so theta doesn't feel left out. So the whole sucker actually factors. So we can split this off as the d theta part and the rho part. That's not rho, what am I talking about? That's phi. Phi! And then the rho part from 0 to 1, e to the rho cubed, rho squared, d rho. And then you can see that the Jacobian rho squared, that is giving that rho squared there. That's exactly what we need to do a u substitution here with u equals rho cubed. Then our du will be 3 rho squared d rho. Move the 1/3 over here. And it's nice and quick to integrate that guy. So we have a 2 pi, and then the integral of sine phi is going to give us 2. And then from this last one, we're going to have 1/3 times e to the rho cubed, evaluated from 0 to 1, which will just give us e minus 1. So putting that all together, we'll have 4 pi over 3 times e minus 1. There's our answer. And just so you're convinced that this was the right way to set up this problem, if you were to look at it in terms of Cartesian coordinates, it would be, let's see, the integral from -1 to 1 of the integral from minus square root 1 minus x squared to positive square root 1 minus x squared of the integral from minus 1 minus x squared minus y squared up to positive 1 minus x squared minus y squared inside the root. And then our usual, the same integrand that we began with, which was e to the x squared plus y squared plus z squared quantity to the 3 halves dz dy dx. Yeah, not likely.